welcome to this module of vibration engineering. So, in this module we will study about the approximate numerical methods used in this vibration. So, you have studied about the discrete system and distributed mass systems. So, in discrete systems there are definite number of degrees of freedom and definite number of frequencies associated with the system, and in case of distributed mass system or continuous systems there are infinite number of frequencies associated in these systems, but all these frequencies are not of importance to the engineers when they are designing the system. So, most of the systems are vibrating with in the lower frequencies. So, if the engineer knows about the few frequencies, few lower mode frequencies, then he will be able to design the system. So, also we studied the methods how to determine these mode shapes and the frequencies of the systems. So, in case of continuous system you can write the solution in this form, that is y x t equal to n equal to 0 to infinity a n cos omega t plus b n sin n omega t into phi n x. So, for nth mode, so the free vibration response of the system you can write in terms of this modal matrix in case of a discrete system, or this modal function in case of a continuous system, and by this time modulation. So, this is the time modulation. This time modulation is a n cos omega t plus b n sin omega t. So, in this case, in case of this continuous system, you may take infinity number of modes to find the solution of this system, but for practical application one need not have to take these infinity number of modes, and he may truncate this series to a finite number. So, by truncating this thing, the error introduced in this system, so one can see that there will not be much error in the system. So, for practical application some approximate methods can be used without finding this exact solution of the system. So, if by taking these approximate method our results is within 5% or within a limited value, then it can be used for the engineering purpose. So, for that purpose this approximate numerical methods has to be studied. So, in the exact methods, so you are finding the eigenvalues of the system and eigenvectors of the system, and in case of continuous systems you are finding these eigenfunctions and the eigenfunctions or the mode shapes of the system. So, in this approximate method we are going to find only the few frequencies. For example, we will find only the fundamental or first and second mode frequencies in these systems. So, we will use different methods. So, those methods include the Rayleigh method, Dunkerley procedure, method of matrix iteration, Holzer method, transfer matrix method, Rayleigh-Ridge method, and Galerkin method. So, these methods can be applied both to the continuous and discrete systems. So, in the series solution we have seen we can approximate the function by truncating this infinity series to a finite number of series, and also the formulation and computation effort can be reduced by truncating the series, and we can do it in 3 different ways. So, the first way is to retaining n natural modes only and considering them as the generalized coordinates and computing n weighting function to best fit the initial condition or the forcing function. In the second case, substituting for the n modes an equal number of known function phi n x that satisfies the geometric conditions of the system, then compute the function phi n. So, this equation I can write it in this form. So, it can be written as phi n t, f n t and phi n x. So, I can take a function this phi n x which satisfy only the geometric boundary conditions, and I will find this f n t which will best fit the initial conditions and other boundary conditions or the forcing functions. Already you know in exact method we are finding this eigen function of the system, but instead of finding these eigen functions which satisfy both the differential equation and all the boundary conditions, I can take some function which satisfy only the geometric boundary conditions, and then I will find this f n t which will best fit the other initial conditions, the differential equation and the forcing function. So, in that way I can approximate the system. The third way I can approximate it by, so let this is the system. So, in this system I can take several points on the system, and taking these physical coordinates are the generalized coordinates of the system, or the displacement of these points I can take, let it is q1, q2, q3 and qn, like that I can take this function by taking these physical coordinates as the generalized coordinates and considering them as function of time. Then I can compute and feed the differential equation and find an equation or expression which will feed the initial and boundary conditions. So, in these three different ways I can approximate the system. So, in the first way I can take the generalized coordinate and I can take these as the generalized coordinates and approximate or find the weighing function f n t. In the second case I can take the function which satisfy only the geometric boundary conditions and find this f n t, and in the third case I can take these physical parameters as function of time and feed the function to find or find the function which will satisfy the boundary conditions and the differential equations at initial and boundary conditions. So, in these three way I can approximate this series. So, let us see the Rayleigh method. So, in case of Rayleigh method, let us consider this discrete system. Let us start with a discrete system. So, let this mx double dot plus kx equal to 0 is the equation for this discrete system. So, for the discrete system, for example, you just take this spring and mass system, this is another spring and mass system. So, this is a 2 degrees of freedom system, and in this case you can write this equation in this form m11 m12. So, the equation becomes m11 m12 m21 m22. So, this is x1, this is x2. So, I can write this as x1 double dot x2 double dot plus similarly k11 k11 k12 k21 k22 into x1 x2 equal to 0 0. So, this is for the free vibration of the system, and we are interested to find the frequency of the system. So, already you know in the exact method I can find it by finding this dynamic matrix, that is M inverse k. First finding this M, this is M matrix, mass matrix, and this is the stiffness matrix K matrix. So, by finding this M inverse k I can find the dynamic matrix A. So, after finding this dynamic matrix I can find the eigenvalue of this dynamic matrix to find the eigenvalues of the system. So, these eigenvalues correspond to the square of the natural frequency, and also after finding this eigenvalue I can find the mode shape or normalized modes of the system, which are the eigenfunctions of the system. So, I can find the eigenvalues and eigenfunction of the system. So, if I am taking this z as the eigenvalue of the system, I will take z as the approximate value. Let me take initially this phi as the eigenvalue of the system. So, phi, if phi is the eigenvalue of the system, so from this expression mx double dot plus kx, so it will satisfy this equation. So, you know, so it will satisfy the equation k. So, then it will be k phi I. So, for the ith mode, so it will be k phi I equal to omega I square. So, it will be equal to omega I square phi I, omega I square m phi I. So, for the ith mode I can write this equation will satisfy, thus this mx double dot plus kx equal to 0 will satisfy that equation, because this x I am assuming it to be harmonic. So, x can be written as phi sin x, x can be written as phi sin t, and so by substituting this x equal to phi sin t, you can write this as minus m omega square phi plus k phi equal to 0. So, minus, so in this equation, so this is your equation mx double dot plus kx equal to 0, substituting x equal to, so let me substitute it is equal to phi sin t, phi sin omega t, then it becomes, so this equation becomes minus omega square m phi plus k phi equal to 0, or I can write this as for ith mode k phi I equal to omega I square m phi. So, from this expression you can write this, or from this I can write the ith mode, I can write it as like this. So, omega I square will be equal to, so by pre-multiplying I can pre-multiply this by phi I transpose, and by applying this orthogonality principle I can write this as, so this will be equal to phi I transpose. So, phi I transpose k phi I by phi I transpose, so T for transpose m phi I. So, this omega I square omega I square equal to phi I transpose k phi I by phi I transpose m phi I. So, here phi I is the exact eigenvalue of the system. So, if you do not know the exact value, we can assume some other value which will approximate this phi. So, in that case, by substituting that approximate function, so I can write this expression in this form. So, I can write this omega I square equal to rz, let us substitute this z as the function arbitrary vector, let us considering this z as the arbitrary vector. So, I can write this as rz. So, then it will be z transpose kz by z transpose mz. This rz, this quotient, this rz, this is known as the Rayleigh quotient of the system, Rayleigh. So, this is known as Rayleigh's quotient. So, when you are taking this z as the approximate function or approximate vector, then this is known as the Rayleigh quotient. So, this Rayleigh quotient will be equal to the actual eigenvalue of the system when this z equal to phi. So, when z equal to phi, so then this function will be reduced to, or this Rayleigh quotient will be reduced to the eigenvalue of the system. So, we know from the linear algebra that any function z or any vector z can be expressed as a linear combination of n linearly independent vectors. So, this is the expansion theorem. So, you can write this z as z I. So, I can write this as C I into z I. or I can write this as ZC, where Z is the square modal matrix. So, Z is the square modal matrix, and by normalizing that thing one can write this as Z transpose MZ. One can normalize the square transpose this matrix. So, Z transpose MZ equal to I. Already you have seen similar cases in case of weighted modal matrix. So, in case of weighted modal matrix P weighted modal matrix transpose. So, P weighted modal matrix transpose M P weighted modal matrix was I. So, here this P was the modal matrix and P weighted modal matrix was obtained from this weighted modal matrix. So, one can find a Z such that this Z transpose MZ will be equal to I. So, when it satisfies this equation, that time one can write this Z weighted modal Z transpose KZ. So, that time Z transpose KZ will be equal to a diagonal element. So, if you recall this P weighted modal matrix K P weighted modal matrix in case of the discrete system. So, you have seen that this matrix is the lambda matrix, or this matrix is a diagonal matrix containing eigenvalue in the diagonals. So, in this case, so if you are taking this Z transpose KZ, so we will obtain a diagonal matrix. So, we will obtain a diagonal matrix with omega square term, or omega 1 square, omega 2 square and omega 1 n square in the diagonal. So, let us assume a vector Z. So, this Z can be written in this form, where Z is the matrix, square matrix, capital Z is the square matrix. So, this capital Z transpose MZ, we can take this Z in such way that this Z transpose MZ equal to I, that is unity matrix, and Z transpose KZ equal to diagonal element omega 1 square, omega 2 square and omega n square. So, if you can find in this way, so I can write this RZ, that is this Rayleigh quotient in this case can be written in this form. So, Rayleigh quotient can be written, so C transpose Z transpose K Z C by C transpose Z transpose M Z C. So, already you know this Z transpose K Z can be written in this as a diagonal matrix, and this Z transpose M Z is the I matrix. So, this is equal to I, and this is a diagonal matrix with omega square in the diagonal terms. So, this thing can be written as, so this will be equal to C transpose. So, if I am writing this matrix as P matrix, this Z transpose K Z, which is a diagonal matrix, let me write this as the P matrix, then I can write this as C transpose P C by C transpose I C, but this is equal to C transpose P C will nothing but this, it will be equal to summation I equal to 1 to n. So, this becomes C I square omega I square by summation of C I square. So, this is I equal to 1 to n. So, this is summation C I square. So, you can verify this thing by taking a 2:2 matrix. Let me take the C equal to C1 C2, then it becomes C1 C2 multiplied by, so you have a unit matrix 1 0 0 1, let us take, and this will be equal to C1 C2. So, if you multiply this thing, then it becomes C1. So, let us multiply the first two. So, this is 2:1. So, this is 1 row 2 column. So, 1 row 2 column, this is 2 row 2 column, and this is 2 row 1 column. So, this becomes, so final expression will becomes 1 cross 1. So, if you multiply this becomes C1. So, this is you will get 1 cross 2. So, if you multiply this becomes C1 and this becomes C2. So, this final expression, so this multiplication will be C1 square plus C2 square. So, this multiplication will be C1 square plus C2 square. So, if you multiply this, then this becomes 1 row and 2 column C1 C2 into C1 C2 into C1 C2. So, this will become C1 square plus C2 square. So, this is the lower part. Similarly, in the upper part you have a diagonal matrix. This is equal to C1 C2 multiplied by omega 1 square 0 omega 2 square, and let me multiply it by C1 C2. So, these are the coefficient of that z we have taken. The z vector we have written in terms of z1 C1 plus z2 C2, like that we have written. So, from that this C1 C2 coefficients you are getting, and if you multiply this thing, then it will becomes omega 1 square C1 square plus omega 2 square C2 square. So, this thing you can write it as summation omega I Ci square, omega I square Ci square. So, this Rz now you can write in this form. So, this becomes, so the expression for Rz you can write Ci square omega I square I equal to 1 to n Ci square. So, in this way you can find, so in this way you can find the expression for this Rz. So, in this expression, so you can now if you select, so let us assume that we have made some error in assuming this z. So, already you know that this Rayleigh quotient you are writing in this form. So, this is equal to I equal to 1 to n Ci square omega I square, and this is equal to Ci square. So, let us assume that this nth mode or some mode differ from this actual eigenvalue. We are assuming this z, and one of the mode or this z0 is, or z differs very little away from the certain eigenvector phi r. Then the corresponding, so let we are writing this z in this form. So, z equal to z1 c1 plus z2 c2, z2 c2 plus z3 c3. Let me write this is equal to zr cr plus zn cn. So, we can write this z vector as a linear combination of this z1 z2 z3. So, in this way, so if this, let this rth eigenvalue, so rth eigenvalue should correspond to this zr. So, if it differs from this, then I can write that this Cr differs from this actual value. So, Ci by Cr. So, let us assume it in this way. So, let it is equal to epsilon I, which is very less than 1. So, when it differs from the particular eigenvalue phi I, so let this R mode differ from this phi I. So, when it differs from this phi I, so I can, so when it differ little from this phi I, the corresponding Cr term, so you note that these terms, so these correspond to different modes, and so these term, this when it differs from this phi I, then the Cr corresponding Cr term will be a large value. So, as the Cr term will be large, then Ci by Cr we can write it equal to epsilon I, as this Cr is a larger term. So, we can write this Ci by Cr equal to epsilon I, where epsilon less than equal to r. So, this expression we can write if I not equal to r. So, when I not equal to r, so we can write this C I by C r equal to 1. So, here we are assuming that this rth mode, so this Z r C r is not equal to phi I, and in that case as it is differing from this particular eigen value or eigen mode. So, we can assume that this C r is very large. So, when you are assuming the C r very large, then the C I by C r will be a small term. So, this will be equal to epsilon, and this epsilon is less than equal to 1. So, we can, so from this R z expression we can substitute. So, let us substitute this expression here, and in this R z expression, so we can write this expression R z equal to now. So, it will be equal to, so if we expand this thing, then it will be C 1 square omega 1 square, C 2 square omega 2 square, C 3 square omega 3 square, and C r square omega r square, and this part is equal to C 1 square plus C 2 square plus up to C n square. So, now dividing this by C r square, so we can write this will be equal to, so by dividing that thing by C r square, I can write this equal to omega r square plus, so this is equal to omega r square plus I equal to 1 to n. So, this will be equal to epsilon I square into omega I by omega r square, and this is 1 plus I equal to, so I equal to n epsilon I square. So, this is equal to epsilon. So, this expression I can write it correctly. So, this becomes C 1 square omega 1 square plus C 2 square, and similarly C r square omega r square. I am dividing it by C r square. So, this becomes omega r square, and other terms, in other terms I will write it C I by C r whole square and omega I square. So, it becomes epsilon I square omega I square. This becomes 1 plus epsilon I square. So, this equal to when I not equal to r. So, when I not equal to r, this Rayleigh quotient I can write in this form. So, you can observe from this, let us take this I equal to 1. So, you can note that this epsilon I square is a very small quantity, and we can write this r 1 z for the first mode I can write, or Rayleigh quotient r 1 z I can write r equal to 1. So, this becomes omega 1 square. So, I can take this omega r square common. So, this is omega n square into 1 plus, so when I am taking this common, so I equal to, as I am finding for r equal to 1, so this will not contain this first term. So, it will be I equal to 2 to n, then epsilon I square omega I by omega 1 square, by here I can write, so this is equal to 1 plus summation I equal to 2 to n epsilon I square. So, from this expression you can note that when we are making an error of, we make an error of 10% in taking the correct value of z. So, in that case the error will be, so this part will be the error. So, for actual eigenvalue, this r1z should be equal to omega 1 square, but if you are taking a 10% error in finding this value, 10% error in this value, then you can see that the error will be of the order of epsilon square. So, the error will be only 1% in this case. So, a 10% error in the form of eigenvector or natural mode will result in only 1% error in the eigenvalue or the natural frequency. So, you just observe that this, in this case I can write that this R1Z always greater than equal to omega 1 square. So, you can observe this, that the Rayleigh quotient is will never have a value less than this first mode eigen frequency. You can note that this Rayleigh quotient is never lower than the smallest eigenvalue. Also, you can see that in a conservative system, the frequency of vibration has a stationary value in the neighborhood of the natural mode. So, from this expression you can see that if you take any other value of this z, so always you will get a value nearer to this omega 1 square. So, you can tell that the vibration has a stationary value in the neighborhood of the natural mode. The vibration has, so you can note this. So, the vibration has a stationary value near the neighborhood of a natural mode. So, this is known as the Rayleigh principle. So, this is known as the Rayleigh principle states that the vibration has a stationary value near the neighborhood of the natural mode. So, in this case you have found this Rz or R1 is nearly equal to or always have a value slightly greater than omega 1 square. Similarly, by taking a mode which is equal to the second mode, you can find this R2z equal to omega 2 square, or if the function or the vector what we have chosen is nearer to the second mode. So, we will get the second natural frequency or we will get a frequency which is slightly closer to the second natural frequency. So, by using this Rayleigh quotient method, we can get the approximate value or approximate eigen value of a system. So, also we can proceed or we can find this value in some other way. So, let us write this expression in this form. So, the total energy of the system can be written in terms of T plus V, that is kinetic energy of the system plus the potential energy of the system. Let you take in the case of a simple pendulum. So, in this case of a simple pendulum, so you know that when it is passing through the mean position, the system, the velocity of the system is maximum or velocity of the pendulum is maximum, and when it is at this end position, the velocity is 0 and all the energy are converted to this potential energy. So, at this position the system has only potential energy, and at this system or at this instant the system has kinetic energy. So, this is maximum kinetic energy and this is maximum potential energy, and at any other time the system has a energy which is a mixture of potential energy and kinetic energy. So, you can write this E equal to T plus V, that is the total energy of the system. Also you can write this as T max maximum kinetic energy plus 0, or you can write this as 0 plus V max maximum potential energy. So, you can write this T max equal to maximum kinetic energy will be equal to V max, maximum potential energy of the system. So, by using this expression also you can find this natural frequency of the system. So, T max equal to V max. So, from this you can write, so let us assume a function certain mode. So, if you assume a certain mode, that is Z, so let Z equal to, I am assuming in this form, Z equal to Z1, Z2, Zn. So, let me assume this mode. So, if I will substitute this in this kinetic energy and potential energy, I can write this kinetic energy term. You know the kinetic energy can be written as half V transpose mv. So, I can write this T max, maximum kinetic energy, equal to half Z transpose m z omega square. So, as it is equal to V transpose mv, and velocity can be written in terms of the displacement, that is omega z. So, by substituting that thing you can write this T max, that is maximum kinetic energy of the system, equal to half Z transpose m z omega square. Similarly, if I are taking or choosing this Z matrix in such way that it will yield this as a unity matrix, and you can write in this way. So, in that case you can write this will be equal to half m1. If I will expand this thing, then it can be written in this form, m1 z z1 square. I can write for the z mode, I can write m1 into z omega into z1 square plus m2 into omega into z2 square. Similarly, you can go on writing this will be equal to mn. So, this will be equal to mn into omega into zn square. So, this is the T max, that is the maximum kinetic energy of the system. So, let you have a system with 3 mass. So, this is one mass, this is the second mass. So, let me add a third mass also to the system. So, this is m1, this is m2, this is m3. So, the kinetic energy of the system will be equal to, so this is z1, this is z2, and you are assuming this is to be z3. So, the kinetic energy will be equal to half m1 z1 dot square plus half m2 z2 dot square plus half m3 z3 dot square. So, assuming z to be in the form of z sin omega t or harmonic. So, you can write this equal to half m omega square z1 square, half m2 omega 2 square z2 square plus half m3 omega 3 half. So, you can write this way. So, half m1 omega 1 square z1 square plus half m2 omega 2 square z2 square plus half m3 omega 3 z3 square, as omega you are taking for a particular value of omega. So, then this is equal to half m1 omega. So, omega z is the velocity, and so for the first mass the velocity is omega z1, second mass it is omega z2, and third mass it is omega z3. So, it becomes this kinetic energy becomes half m1 omega square z1 square plus half m2 omega 2 square z2 square, and for this half m3 omega square z3 square. Similarly, for n system you can write this kinetic energy in this form. So, now we have to guess this value z1, z2, z3. So, in this case I can take the static vibration, or this will be proportional to m1g, this will be proportional to m2g, the displacement of this will also proportional to m3g. So, in this static deflection, so we can find this potential energy of the system. So, the potential energy I can write in this form. So, V max will be equal to, so m1 g1 z1 plus m2 g2 m2, so m1 g z1 plus m2 gz plus mn gzn. So, this way we can write this kinetic energy and we can write the potential energy of the system. Now, we can equate this and we can write this omega square in this form. So, it will be equal to g into I equal to 1 to n. So, this will be mi zi and this will be equal to half I equal to 1 to n mi zi square. Already we got this kinetic energy in this form, that is equal to half omega square into m1 z1 square plus m2 z2 square plus mn zn square, and this potential energy if you are writing in this form m1 g z1 plus m2 g z2, and for nth mode you are writing this equal to mn. So, for other modes also you can add it. So, you can add, and for you can write mn g zn, then this equating this kinetic energy and potential energy you can write this equal to g mi zi. So, summation I equal to 1 to n mi zi half mi zi square. So, in this way you can find, for a discrete system you can find the Rayleigh quotient or the eigenvalue of the system or the approximate eigenvalue of the system by equating the maximum kinetic energy equal to this maximum potential energy, or by directly writing this formula, that is Rz equal to, so you can write this as Z transpose Kz by Z transpose Mz. So, by writing from this expression or from equating the kinetic energy, maximum kinetic energy equal to maximum potential energy, you can find the frequency of the system. So, for a continuous system, so for a continuous system you can write this u max, that is the maximum potential energy, like this. So, it is equal to half 0 to L E I del square y by del x square whole square dx, and this T max equal to half omega square 0 to L y square dm. So, here you may take this y as the static deflection of the continuous system. So, by taking the static deflection term, by equating this u max equal to T max or maximum potential energy equal to maximum kinetic energy. So, you can write this omega square equal to, so this is equal to 0 to L E I del square y by del x square whole square by 0 to L y square dm. So, when this y matches with the eigenvalue of the system, then you will get the exact eigenvalue, and when it is not matching with this eigenvalue, you will get the approximate value, and already we have seen that this approximate value. So, if you make a error 10% error in taking this eigenvector, then there will be 1% error in finding this eigenvalue, or this eigenvalue you can get it of the order of epsilon square. So, one can predict accurately by using this Rayleigh method the fundamental frequency of the system. So, let us take some example. So, as a first example, let us take a discrete system. So, let in this discrete system we want to find the eigenvalue of the system. For example, let us first take this simple system with k and m. So, in this case already you know the eigenvalue or the natural frequency of the system equal to root over k by m. So, the same thing you can find it using this Rayleigh method. So, in the Rayleigh method you can have this maximum kinetic energy equal to half k x max square. So, this will be equal to half m x dot square. So, x dot, assuming this x to be in the form of a sin omega t. So, you know your x dot equal to a omega sin omega t. So, this is x dot will be equal to a omega cos omega t. So, as x equal to a sin omega t, you have x dot equal to a omega cos omega t. So, this maximum potential energy will be equal to half k x square. So, x will have a maximum value that is equal to a. So, this becomes half k a square. So, this is the maximum potential energy of the system. So, this will be equal to maximum kinetic energy. So, the maximum kinetic energy, so maximum velocity will be a omega. So, maximum kinetic energy of the system will be equal to half m a square omega square. Now, equating these two terms, so you can find, so half cancel. So, this a square cancel. So, this omega square you can write equal to omega square equal to k by m. So, omega equal to, so or omega equal to, in this case you have found omega equal to root over k by m. So, this is the natural frequency, that is why I have written n. So, in this way you can find, and let us take a system with two mass. So, this is the fast spring and mass, let it is k and m, let us take same mass and stiffness. So, this is m and k. So, in this case I can take the static mode like this. So, due to, so this will have a weight of mg and this is this has a weight of mg. So, 2 mg weight is acting on the spring k. So, it will have a displacement of 2 mg by k. So, let me take this is the line. So, the displacement will be 2 mg by k in this case, and this mass will have a displacement of, so this spring is subjected to a weight of mg. So, this will have a displacement of mg by k, and already you have displacement of 2 mg by k. So, total displacement of the second mass will be equal to 3 mg by k. So, by taking the static deflection, so I can take this is equal to 3 mg by k. So, the deflection plot I can show it in this way. So, this is 2 mg by k and this is 3 mg by k. So, I can take this Z1 equal to 2 mg by k and Z2 equal to 3 mg by k in this case. So, the fast mode, when it is vibrating in the fast mode, I can take the I can take this approximate vector as 2 mg by k and 3 mg by k. So, when it is vibrating in the second mode, so this is for the fast mode. So, these are the approximate function I can take. In the second mode, I know that 1. So, in the fast mode both the masses are moving in the same direction, and in the second mode the fast mass and the second mass will move in opposite direction. So, when they are moving in opposite direction, so I can let me keep the fast mass same, that is 2 mg by k, but the second mass will move in the opposite direction. So, I can take this is 2 mg by k, and for the second mass I can take it as minus 2 mg by k. So, in this case, so I have taken the static deflection for the mass 1 as 2 mg by k, and for the second mass it equal to 3 mg by k for the fast mode, and for the second mode, as I know both the masses are moving in opposite direction, I can choose it in this way. So, by choosing it in this way, so I can write the kinetic energy of the system and the potential energy of the system. So, I can write T max, maximum kinetic energy will be equal to half m1 x1 dot square plus half m2 x2 dot square. So, this will be equal to, so the maximum velocity equal to x2 dot square, maximum velocity will be equal to a omega. So, I can write for the fast mass maximum velocity equal to a1 omega, and for second mass it is equal to a2 omega. So, the maximum will be equal to, as I am taking this mass are same, it will be equal to half m a1 square plus a2 square. Similarly, I can find this V max, maximum velocity, maximum potential energy. So that will be equal to half k x1 square plus half k x2 square. So let us see the, so this spring has a displacement of, so this is x1, this is x2. So this spring will have a displacement of x1, but this spring will have a relative displacement of x1 and x2. So this will be x2 minus x1. So it will be, so in case of second spring the displacement is k x2 minus x1 square. So the total potential energy of the system becomes half k x1 square plus half k x2 minus x1 square. So by substituting the maximum value of x1 equal to a1 and x2 equal to a2, I can write this as half k, this will becomes a1 square plus, so this becomes a2 minus a1 whole square. So in this way I can write, or I can equate this. So this is this kinetic energy is multiplied by half m a1 square plus a2 square omega square, as velocity equal to velocity, maximum velocity equal to a omega. So it can be written half m a1 square plus a2 square omega square. So I can equate this maximum kinetic energy with this maximum potential energy. Here I am assuming a1 equal to, so a1 I have assumed equal to 2 mg by k and 3 mg by k equal to a2 for the first mode, and for the second mode a1 I have assumed equal to 2 mg by k, and for the second mass it is equal to minus 2 mg by k. So I can write this omega square expression for omega square, this will be equal to half k a1 square plus a2 minus a1 square by half m a1 square plus a2 square. So this half cancel, so this becomes a1 square plus a2 square, I can delete this half. So this becomes omega square equal to this k by m a1 square plus a2 minus a1 square by a1 square plus a2 square. So now substituting for the first mode, so let us find for the first mode. For the first mode, so I can substitute this a1 equal to 3 mg by, so a1 equal to 2 mg by k and a2 equal to 3 mg by k. So by substituting it in this expression, then this becomes a1 square plus, so I have this expression omega square equal to a1 square plus a2 minus a1 whole square by a1 square plus a2 square into k by m. So I can have it like this. So for a1 I will put 2 mg by k, so this becomes 4. So if I will take this mg by k common, mg by k square common, then it will becomes a square, so it will become 4. So then plus 4 plus a2 minus a1, a2 minus a1 will give, so this is 9, 3 minus 2 this is 1, so 3 minus 2 square it is equal to 1 square, and below it is equal to a1 square, that is mg by, so this becomes mg by k whole square into, for a square I can write this is equal to 4 plus this is equal to 9. So in this way I can cancel these two terms. So this becomes, so in the, so this becomes 5 by 13. So this 5 by 13 will give me, so 5 by 13, so we are getting a value of 0.384. So this is equal to 0.384 k by m. So, this omega you can, so this is omega squares or omega 1 square. So, you are finding it for the first mode, or omega 1 will be equal to root over this. So, this becomes 0.62 root over k by m. Similarly, you can find omega 2. So, in this case omega 2 square will be equal to mg by k whole square, mg by k whole square into. So, for second mode you are taking this A1 equal to 2 mg by k and A2 equal to minus 2 mg by k. So, it will becomes, then it will become this A1 square will be 4. So, this will be 4 plus A2 minus A1, that is minus 2 minus 4. So, minus 4 whole square, this becomes 16. So, 4 plus 16 here you are getting, and below you are getting this is 4 plus 4. So, 4 plus 4, this is 8. So, for the second mode you are getting omega 2 square. So, this is also mg by k whole square. So, this cancel. So, omega 2 square you are getting equal to 20 by 8 k by m. So, 20 by 8 will give you 2.5. So, you are getting this is equal to 2.5 k by m. So, in this case this omega 2, this is equal to 2.5 root over. So, it becomes 1.58 root over k by m. So, you are getting the second mode frequency equal to 1.58 root over k by m, and the first mode frequency equal to, so the first mode frequency we got it equal to 0.62 root over k by m. So, you can see this omega 1 exact value are like this: omega 1 square equal to 0.36 k by m and omega 2 square equal to 2.64 k by m. So, these are the exact value, and in this case we obtained this omega 1 square equal to 0.38 k by m and omega 2 square we obtained equal to 2.5 k by m. So, you just note that by taking the static deflection we obtained very close to this first mode and second mode frequency. Here the first mode is 0.36 and here we are getting it is equal to 0.38, and in case of the second mode the eigenvalue is 2.64, exact eigenvalue is 2.64, and here we are getting 2.5. So, if you calculate the error, so you can find 2.5. So, minus 2.64 by 2.64 you can divide that thing and you can obtain the error only. So, 0.05 you are getting. So, if you multiply this thing, so you are getting in the second mode 5% error, and in the first mode, so it is 0.02. So, 0.36 minus 0.38, so 0.02 by 0.38 you can make. So, this is similar. So, you can see the error only in the second decimal only. So, in this way you can find the fundamental frequency of the system by using this Rayleigh method.